All right, section 3.1, we're going to be learning about exponential functions and their graphs. All right, so we're continuing with exponents and some exponential properties. So we have the one-to-one property. So when a is greater than 0 and a is not 1, if a to the power of x is equal to a to the power of y, then x and y are equal. So we'll do some examples where we actually put numbers, and this will make more sense. But if our bases are the same, we can just cross out the bases and just set the exponents equal to each other. And then also don't forget, anything raised to the power of 0 is 1. So if I had 5 to the power of 0, what would that be? 1. Thank you for paying attention. All right, so our goal when solving these is to get them to have the same base. That way we can cross them out and set the exponent parts equal to each other. So for a, I can't change the value of one of these numbers, but I can change the way that one of them looks. So is there any way that I could change one of these to have the same base? Awesome. I can change 9 to 3 squared. 3 squared is still 9. I'm not changing the value of it. I'm just changing the way it looks. I just want it to have the base of 3. So once my bases are the same, I can cross them out and just set the exponents equal to each other. So I have x minus 2 is equal to 2. And then solve for x. So we would add 2 to both sides. So x is equal to 4. Perfect. Any questions? Right, let's look at B. So we want to do the same thing here, but remember, we don't want to change the value of something, we just want to change the way that it looks. So what do you think I can do? So a negative exponent flips whatever the number is. So I could change this to be a negative x and just make it so like 2 to the negative x power. So I made my exponent negative and just flipped it. Is there a way that I could have 16 with the base of 2? So 2 to some power would be 16. 2 to the 4th power. So I changed this to be 2 to the 4th power. So now once my bases are the same, I can cross them out and just set the exponents equal to each other. So negative x is equal to 4. And then solve for x. So I divide both sides by negative 1. X is equal to negative 4. You can always check your work by just plugging it back into. So if I plugged in negative 4 into x from the start, I'd get 16. Any questions here? All right, let's look at C. So 6 to the power of x is equal to 1. What can I do? How can I make these have the same base? Well, on the last page, I said, what exponent makes my number 1? The exponent of 0. So I could change 1 to be 6 to the power of 0. Because 6 to the power of 0 is 1. And then what do I do once my bases are the same? Cancel them out. So I could say x is equal to 0. All right, so next thing we're going to look at is the natural base e. So e is just a number in our calculator. Everybody's calculator, unless it's just a 4-function calculator, but most everybody's calculator has that button e. So it's kind of like pi, where it's just a predetermined value. It's kind of, we just treat it as a variable almost, but it's just e. It's a number. So e to the power of x is called the natural exponential function. So in the first part, we were graphing things like 4 to the power of x. We can also graph e to the power of x. We just have to use our calculator to evaluate the numbers. So this slide talks about where e comes from. It's not important, so we can skip it. So example 7. We're going to use a calculator to evaluate the function f of x is equal to e to the power of x at each value of x, round 3 decimal places. So here, we just need to plug in x. So I have e to the power of 4.2. Make sure you know how to use your calculator. Everybody's calculator is a little bit different. On the quiz, you're not going to be able to use your phone calculator. So make sure you have a calculator and you know how to use it. So on my calculator, I click E, and then I have a little caret button, that up arrow, and then I would click 4.2 equals. There's actually a button on the calculator that says e to the power of x, but before I click that, I have to click shift. So I would click shift here. So shift e to the power of x, and then you just put 4.2 equals. So if you do it right, you should get 66.686. And it says 3 decimal places, yeah. So that would be our answer. All right, for B, there's a little bit more math going on. We just have to make sure we follow our order of operation. So 125 e to the power of 0.05 times 30. So I have to do what's in the exponent first, so I would do 0.05 times 30. So that would give me 1.5. And then e to the power of 1.5. So that would be 4.4816. I'm just going to leave it in my calculator to do the last step, so my answer can be as exact as possible. So just leave that in the calculator and multiply it by 125. So 560.211. All right, example 8 says use a graphing utility to construct a table of values for the function, then sketch the graph of the function. So just like I graphed for my exponential functions, I'm going to plug in numbers and plot those points. So I'm going to plug in values for x, put them into my equation, and get values for y, which would be my coordinate points, so x comma y. So what are some good numbers to plug in for x? 1, 0, and -1. Always good numbers. So if I plug in 1, I have 4 times e to the power of 3. So I'd have to put that in my calculator. Have to do e to the power of 3 first and then multiply it times 4. So we get 80.3. So I plugged in 1 and got 80.3. Now this is way, way, way off our graph. So let's plug in 0, see if we get some smaller numbers, because then that maybe we should plug in numbers that are smaller and get some numbers that we can clearly see. So let's plug in 0. I have 4 times e to the power of 2. That gives me 29.5. So I plugged in 0, got 29.5. We're a little bit closer. So let's plug in -1. I have 4 times e to the power of 1, because -1 plus 2 would just be 1. So this would be e to the power of 4. No, e to the power of 1 times 4. We get 10.8. So I plugged in -1 and got 10.8. If your numbers are this big, my suggestion would be to keep plugging in numbers. So let's plug in -2. 4 times e to the power of -2 plus 2 would be 0. What's e to the power of 0? 1. Anything to the power of 0 is just 1, and 1 times 4 would be 4. So this is a little bit better. I plugged in -2 and got 4. And then let's just plug in one more, say -3. So I have 4 times e to the power of -1. Which would be 1.47. So I plugged in -3 and got 1.4. So we can graph our points. So I'm going to go to the left to -3, up 1.4. I go to the left to -2 and up 4. And I would go to the left to -1 up 10, which is way, way, way off our graph. So our graph looks like this. What do you think my horizontal asymptote is? So throwing it back to what we did on Friday. Awesome. Our horizontal asymptote is always y is equal to 0. Remember, it's a line, so you need that y is equal to. Unless I have a vertical shift. So if I'm adding or subtracting a number on the outside, that changes my horizontal asymptote. But here I'm not, so my horizontal asymptote stays at y is equal to 0. Do I have a vertical asymptote here? What do we think for exponential graphs? Do we have a vertical asymptote? No. For exponential graphs, we don't have a vertical asymptote. And then what is my y-intercept? So we can't clearly see where we cross the y-axis here, but how did I find my y-asymptote? My y-intercept, I'm sorry, my y-intercept. I plugged 0 in for x, so I already did that here. I plugged 0 in for x, so what is my y-intercept? 0, 29.5. All right, next we're moving on to compound interest. So we have compound interest versus continuous compound interest, which are two different formulas. So if I had an example that said after 2 years, the balance A in an account with principal P and annual interest rate R, which is in decimal form, is given by the following formulas. So our compounded interest is this one, where P is the principal, so that's the starting amount. It'll usually give you, it'll say principal, or you start with this much. So that's what we start with, the starting amount. N is the number of times per year that it's compounded. So number per year. Some examples would be if it said compounded, let's say annually. If it's compounded annually, how many times does that happen a year? Once. What about semi-annually? Twice. What about quarterly? What about daily? 365. And what about weekly? 52. There are 52 weeks in a year. So these are the common ones you may see. So your N will change depending on the wording of the question. We also have R, which is our rate. So that is the rate, but it is the decimal version. So if my rate was 50%, what is the decimal version of 50%? 0.5. We just move the decimal twice. What if my rate was 5%? 0.05. What if my rate was 5.5%? 0.055. So just be careful. When you're plugging in the rate, it has to be the decimal version. And just move your decimal 2 places. And then lastly in our equation we have T. What do you think T is? Time. So that's how many years you have. how many years it gives you. It'll tell you compounded over 8 years, then your t would be 8. All right, the second formula is whenever it says compounded continuously, so it'll say continuously compounded continuously. That word continuous will be in the question. If it says compounded continuously, you're using this formula, which is A PERT. So A is the amount. P is the starting amount, what you start with. What do you think E is? E is the natural base. So E is just the button in the calculator. You're not going to plug in anything for E. It's just the button in the calculator we use. R, again, is our rate. But it has to be the decimal version, again. And then T is time. So these are the questions that you definitely will need your calculator for. So for the first 3, we're going to use our first formula, which is what comes next? One plus what? R over N to the power of NT. And then the last one, that's when we use our PERT formula. P times E to the power of RT. So that's just the last one. All right, so for A, my question says, find the accumulated value of an investment of $15,000 for 2 years at an interest rate of 3.2% if the money is compounded semi-annually. So semi-annually happens how many times a year? 2 times a year. So N is equal to 2. What's my P? So principal, the starting amount. How much money am I starting with? 15,000. What's my R? 3.2%, but what's the decimal version? 0.032. We said N is 2, and what's T? How many years? 2. So let's plug everything in. So I have 15,000 times 1 plus 0.032 over N, which is 2, times 2 to the power of 2. To the power of 2 times 2. What do you think I have to put first in my calculator? If you were doing this question, where would you start in the calculator? Start with the parentheses, but what in the parentheses? The division in the parentheses. So follow your order of operations. As a reminder, it's PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. So we start with the parentheses, but we have a division going on in the parentheses first. So 0.032 divided by 2, and then we add 1 to it. So inside our parentheses, we should get 1.016. And that is to the power of 4 times 15,000. So next, I'm going to do the exponent. So 1.016 to the power of 4. So that gives me 1.06555. I'm going to leave that number in my calculator and then just multiply it by the 15,000. So the very last step is to multiply times 15,000. And we get 15,983.286, which would round to 29. Let's look at B. So I need to find my principal, which is going to be the same. So principal, rate, and time are all the same as the one before. So 15,000. My rate is what? So 0.032. My time is 2 for 2 years. But compounded quarterly, how many times does quarterly happen in a year? 4. So n is 4. And then we plug everything in. So 15,000 times 1 plus r, so 1 plus 0.032 divided by n, which is 4, to the power of n times t, so 2 times 4. So the first thing I want to do is inside my parentheses, I have to divide. So I'm going to put that in my calculator. 0.032 divided by 4. And then plus 1. So inside my parentheses, I get 1.008. What should I do next? Put it to the power of 8. Awesome. So raise that to the power of 8. So that should give you 1.0582. And then last step, we just multiply. So times 15,000. So it should get 15,987.31. C is the same thing. Compounded monthly happens how many times a year? 12. So n would be 12. So we could do the same thing, just plug in 12 for n. But let's do the compounded continuously one. So our PERT formula. So I need to figure out what P, R, and T is. So what's my P? 15,000. What's my R? So 0.032. And what's my time? 2 years. We plug everything in. So I have 15,000 times E to the power of 0.032 times 2. What do I have to do first? The exponent. I need to multiply my exponent first because I have 0.032 times 2 in the exponent. So 0.032 times 2. And then I do e raised to that power. So we should get 1.06609. And then last step is we multiply that times 15,000. So 15,991.3. It says 385, so it would round up to 39.